In this video, we will look at some examples of how quadratic equations can be used to solve problems involving the Pythagorean theorem. As a reminder, we will use the same 4 steps for solving application problems that we have used in the past. Define variables, translate into an equation, solve the equation, and clearly state the answers. Let's look at our first example. A rectangular flower garden has a width of 6 feet and a length of 13 feet. What is the distance from one corner of the garden to the opposite corner? Round to the nearest tenth if necessary. Let's begin by making a quick diagram. The garden is a rectangle with a width of 6 and a length of 13, and we're interested in the distance from one corner to the opposite corner. Since that's the unknown we're interested in, let's label it with a variable and be clear to define that variable. Let x equal the diagonal distance, and that's measured in feet. As we examine the diagram, we can see that we have a right triangle, and so the Pythagorean theorem could be used to write an equation relating the lengths of those 3 sides of the triangle. Remember that the sum of the squares of the legs, 6 and 13, is equal to the square of the hypotenuse, which in this case is x. So we have the equation 6 squared plus 13 squared equals x squared. And if we simplify a bit, we arrive at the equation 205 equals x squared. Now we can solve this equation by applying the principle of square roots to say that x is equal to positive or negative the square root of 205. Now, although there are 2 solutions to this quadratic equation, only one of them is reasonable in terms of the length of a flower garden. That would never be negative. So we can apply the positive solution, which is approximately 14.3. And thus we can answer the question posed in the word problem to say that the distance from one corner to the opposite corner is about 14.3 feet. Let's look at one more example. The lengths of the legs of a right triangle are consecutive even integers. If the hypotenuse is 10 inches, find the lengths of the legs. Again, we'll round to the nearest tenth if necessary. This problem involves a right triangle. Let's draw one and label the sides. We know that the hypotenuse is 10 inches. The length of the legs are both unknown, but we do know that they are consecutive even integers. So if we let x equal the shorter leg, measured in inches, then the next consecutive even integer after x could be represented by x plus 2. So we'll use that expression to represent the longer leg, again measured in inches. Labeling these on the diagram, we now have the 3 sides of our right triangle, and we can use the Pythagorean theorem to write an equation for this triangle. We have x squared plus the quantity x plus 2 squared equals 10 squared. Simplifying the left-hand side, as we multiply x plus 2 times x plus 2, we would get a perfect square trinomial, which is x squared plus 4x plus 4. And then on the right-hand side, we have 100. Let's write the equation in standard form. So we have 2x squared plus 4x, and then if we subtract 100 on both sides, we have minus 96 equals 0. We can write a slightly simpler version of this equation by dividing both sides of the equation by 2, since all the terms are even. So now we have x squared plus 2x minus 48 equals 0. That trinomial can be factored as the product of 2 binomials, x plus 8 and x minus 6. So we find two solutions to this quadratic equation. Either x equals -8 or x equals 6. -8 is obviously an unreasonable solution for the length of a triangle. So we'll keep the solution x equals 6. So we can say that the shorter leg is 6 inches. And then since the longer leg is 6 plus 2, the next consecutive even integer, we can state that the longer leg of this triangle is 8 inches.